Let's dive right into this explainer. Over the past few weeks, we've been tossing around a bunch of fascinating technical thoughts. Stuff about continuous time recurrent neural networks, physical isomorphism, and the wild world of analog computing. Well, today we're taking all of those scattered fragments and pulling them together into one unified discussable prototype. We're looking at FACS version 0.1, a visionary framework by Lansing Chang. Now, keep in mind, this isn't some rigid product spec sheet with all the final answers. Think of it more as an open presentation, an invitation, really, mapping out the very future of human-machine conversational systems. It all centers around one seriously provocative question. What if the computer itself is the nervous system? What on earth should the interface look like? That question right there sets the stage for a massive paradigm shift. For decades, we've treated computers like fancy calculators. We just feed them discrete instructions. But if the hardware actually mimics the continuous living flow of a nervous system, the way we talk to it has to fundamentally change. It literally challenges the entire foundation of how we interact with machines. So here's our roadmap for today. We'll start with the core friction, move into the radical concept itself, then break down the architecture mechanics. After that, we'll tackle the engineering challenges of weight mapping, look at the analog inference advantage, and finally wrap up with an open invitation. Let's get into it. All right, part one, the core friction, specifically our current digital limitations. To really get this, we have to look at the elephant in the room. Right now, our digital chips are basically just faking a continuous physical world by chopping it up with discrete clock cycles. We're forced to use these rigid, highly constrained commands, and we have to prove who we are with easily copied passwords. There's no true long-term memory or physical role adaptation. But an analog framework, that is a whole different beast. It operates purely on continuous physical dynamics. In this world, your identity isn't a password, it's a physical unclonable function, or a puff. That's a unique physical signature baked right into the hardware itself. It's fluid, and it naturally evolves. Which brings us perfectly to part two, the radical concept, FACS version 0.1. Okay, this is where things get genuinely wild. In this system, there is zero distinction between computing and communicating. They are the exact same physical process. Imagine a conversational system where your dialogue isn't just data being sent to a processor to be crunched. Instead, the conversation itself literally alters the physical constraints of the network in real time. The changing physics of the chip is the conversation. It acts as a full analog nervous system. So how do you even begin to build that? Let's hit part three, architecture and mechanics, the 5 layers. We're essentially building from pure hardware at the bottom all the way up to emergent, almost living behavior at the top. Down at layer 1, you've got your physical arrays, the literal hardware flesh of the neural network, and those unique PUF identities we talked about. Move up to layer 2, and that sets the behavioral boundaries. Layer 3 is super cool. It lets the system instantly self-calibrate. Then we hit layer 4, the conversational interface. This is where your voice actually redefines the system's boundaries. But layer 5, that is where the absolute magic happens. Over time, the physical parameters naturally drift, and the behaviors the system uses most often become its default. The system literally learns, adapts, and solidifies its role over time. It basically grows up. To really wrap your head around what's happening at that base physical layer, let's picture a 3D phase space graph. Imagine a green dot representing the moment the chip powers on, and a red star representing its fully relaxed, steady state. In a normal chip, getting from that green dot to the red star takes thousands of math equations crunched cycle by discrete cycle. But here, the chip's computation is literally just this physical trajectory unfolding in real-time space. The electrical voltages are simply relaxing naturally into their steady state. The physics itself is the math. No algorithms required. Of course, it's not quite that easy in practice. Part 4, the engineering challenge of weight mapping. You might be wondering, how on earth do you map digital weights to analog circuits without environmental noise totally ruining everything? Well, you start in a standard digital environment, like PyTorch doing normal 32-bit training. Then, you discretize those down into simpler 8 or 10-bit digital codes. An on-chip converter then translates those codes into specific gate bias voltages. And those voltages are what determine the synaptic strength, or the connection, between nodes directly on the silicon. But as we know, physical analog circuits are incredibly messy and nonlinear. That messy nonlinearity is exactly why this next feature is such a massive game changer: real-time adaptive calibration. Look, achieving absolute perfect precision in analog hardware is basically impossible because of temperature shifts, voltage changes, and tiny manufacturing quirks. So instead of fighting physics, this 28-nanometer test chip is designed to literally know itself. It has an embedded loop that constantly measures its own physical curves post-fabrication and reverse corrects the codes on the fly. It essentially calibrates out its own flaws, squashing the weight error to under 1%, no matter the conditions. And when you get that working, the payoff is huge. Part 5, the analog inference advantage. Let's break down this division of labor. We keep the heavy lifting, the training, strictly in the digital world. Trying to do complex backpropagation in analog is just brutally hard right now, so we stick to GPUs for that. But for inference, for actually running the model out in the world, we unleash the raw, clockless speed of analog physics. When the model runs, every single node on the chip updates simultaneously. There is no central clock scheduling telling things when to go. It is true 100% parallel computation. And the resulting numbers? They're absolutely staggering. Think of this as a highly specialized coprocessor for edge sensors. The 28-nanometer test chip sips less than 20 milliwatts of power. Compare that to a GPU chugging multiple watts. The inference latency drops to below 25 nanoseconds. And because raw continuous sensor signals flow straight into the analog chip without needing to be chopped up into digital bits first, your discretization loss is literally zero. Now, to be clear, this isn't meant to replace a massive GPU cluster for training language models. It's designed to perfectly fill the gap where GPUs totally struggle, like instantaneous real-time edge processing. Which leads us directly to our final section, Part 6, an open invitation. Like I mentioned at the start, this explainer isn't a pitch for a finished, boxed-up product. It's a foundational concept and a genuine invitation to collaborate. Right now, we're in the software simulation phase, running Python cores and using Unity and Unreal demo scenes to visualize how these behaviors map out dynamically. But the roadmap heads straight toward a revolutionary full-chip reality. The very next step is building an FPGA USB accelerator to validate those insane latency drops. And the ultimate goal? The QCell-G full-chip realization, which keeps all this emergent dynamic behavior but cranks the processing speed up by a factor of 1,000. So I want to leave you with this profound thought to wrap up our explainer. The analog chip doesn't calculate the answer, it becomes the answer. This whole presentation was put together as an open question to the community. If you've got thoughts, doubts, or if you're fired up about the idea of a system where the computer itself is the nervous system, you are highly encouraged to reach out to linsingcheng@gmail.com. Seriously, think about it. If a chip simply becomes the answer through the pure physics of its hardware, how is that going to change the software you build tomorrow? Thanks so much for exploring this wild prototype with me.